Justin Miller, Astronaut College Physics here. Gotta be a little bit careful, but ultimately, hey, let's just go ahead and look at something, shall we? What is this? Well, it's a little tube full of gas, and it's hooked up to source potential difference, and what happens when I flip it on? Ooh, it starts glowing. Because, well, if I excite the gas, we say, and it glows some color. Great. Well, this is actually hydrogen gas in this little glass tube here. And what we want to do is understand the hydrogen atom. And it was observation similar to what we're going to kind of be looking at here early on that drove people to think of things in a different way on a quantum type of level, if you will. So, what happens? We got this light, right? This light that is being produced by the hydrogen gas itself. What would happen if we took a diffraction grating and we passed it through this light? I don't think this will come through that good here, but if I move this across, there may be a point where you see kind of a dark red line, and maybe a blue line, and maybe some purple, and maybe you see a little rainbowish too. Rainbow's due to the white light that we've got going on. But we've got this really dark red line and this really nice blue line, and there's some violet in there too. If I turn this off and do the same thing, don't see anything. You just got that little rainbow effect from this ambient light. So again, not sure if you can really see that, but I'll throw up a picture of what would be seen so you can see it better. What happens when you pass light emitted by a hydrogen gas through diffraction grating? Well, we know what diffraction gratings do. They go ahead and take some composite light source and break it up into the individual wavelengths of which it's composed. Break it up into its spectrum, right? So what's going on with this hydrogen gas? There are specific wavelengths of light that it's emitting, and only specific wavelengths of light. Unlike incandescent light, light from the sun or from a candle, or an incandescent light bulb that produces all wavelengths of light, the hydrogen gas is only producing certain wavelengths. And it's those wavelengths and their intensities that mix together to give hydrogen gas that kind of pinkish, purplish hue that we see. But that's the combination of, really there's 4 discrete wavelengths in the visible spectrum. That's hydrogen. All right, so we want to be able to understand that. Do this without burning myself. Let me take another gas here. I'm going to take, what is this? We'll save that one. I'm going to take this gas here. Another gas. It's not hydrogen. Turn it on. Whoa. That's right. That's neon. Neon, you've heard of neon signs. This is neon gas. And if we were to pass this diffraction grating through it, we'd see that there's a whole bunch of these wavelengths of light that this is emitting. But they're still discrete. It's not a continuous spectrum. And all those wavelengths add together to produce this sort of really obnoxious orange color. But that's neon. We could take another gas, like this, and put it in, and see what happens to it. I'm okay. This is krypton. Krypton, we excite it. It's one of the noble gases. We excite it, and it produces this color light. If we looked at its spectrum, we would see specific wavelengths that it produces in the visible spectrum. What it turns out is that every gas that we would look at has its own signature, has its own discrete spectral lines that it produces, its own discrete wavelengths that it emits. And what we want to be able to do is understand that. This was a question that was wanting to be answered way back. And there was some really intelligent people that kind of tackled this problem and said, well, let's try to understand what's going on more of a fundamental level, on an atomic level. So at this time, it was known that, hey, there's atoms, there's protons, there's neutrons, there's electrons, but it wasn't understood exactly what was going on a fundamental level there. So there were some problems that arose with certain models of the atom. One of the models said, yeah, you've got this proton and maybe a neutron, but you got a proton and you've got this electron that is orbiting it. But the problem with that would be that for light to be emitted, the electron would be falling all the way into the proton, and you'd get a continuous spectrum, and eventually we've got that the electron collides with the proton and then nothing else is happening. That obviously wasn't the case, and there was some holes in that idea to begin with. But it was understood that there had to be some sort of action going on regarding the proton and the electron in a hydrogen atom. And that could be subsequently sort of relayed into other more complicated atomic compositions. So there was a man named Niels Bohr that came along, and he produced some postulates, known as Bohr's postulates, and said, hey, if this is the case, and this is the case, and this is the case, then this is what's going to happen. And his postulates, together with some understood theory about light and atoms themselves, was then utilized to predict successfully the wavelengths of light that would be emitted by the hydrogen atom. And that was really powerful because it gave a clear picture of what was going on, again, on a fundamental level. And that's what we want to do. We want to understand things. So what we're going to concentrate our attention on at this point is Bohr's theory of the atom. And even though not totally correct, it does allow us to understand quantization, discrete energy levels, discrete states at which something can exist at. And that's what this kind of delves off into the realms of quantum mechanics. This is kind of the stepping stone into quantum mechanics itself. So, let's look at this. Bohr's model of the hydrogen atom. So, again, he utilized some things that were already theorized or known to some degree. But Bohr basically said, hey, we've got a proton here. Hydrogen's the simplest atomic system there is, the most abundant element in the universe, at least that we know of. And yeah, it's a single proton and a single electron system in its neutral state. So we've got this proton, and then we've got this electron, and the electron orbits the proton in a circular orbit, and well, kind of started with this. So we have an electron, orbits the proton, circular path. All right, so Bohr came along and said, hey, well, why would it be orbiting? What's holding it in that orbital position, right? What is allowing this object to remain constrained in this circular path? And well, it seemed to be reasonable that there had to be some centripetal force, and that the centripetal force had to be manifested through some charge-charge interaction, Coulomb's law, right? So, postulates here. We have that the electron orbits the proton in circular paths, and the centripetal force is produced by the Coulomb force of interaction. So I kind of started writing it, I'll just write it again. Electron orbits proton in a circular path. Turn this back on. And centripetal force, which constrains the electron, is due to the Coulomb force of interaction. All right, so what does that really say? Well, this electron has some sort of, let me try to make this a little bit more circular. So electron would have some sort of tangential velocity, the tangential, depending on where it is, it points in different ways, but that's basically its orbital speed. And then what do we have to have? We have to have some centripetal force there that's responsible for the angular, that's responsible for the centripetal acceleration that correlates with the centripetal force. That was redundant, but get the idea here. Centripetal acceleration needed to continuously change the direction of the velocity vector. That's what the centripetal force is all about. And he said, Bohr said that centripetal force has to have the same correlation, or has to be equivalent to the Coulomb force of interaction between the proton and the electron. So, we'll say the magnitude of centripetal had to be equal to the magnitude of the Coulomb force. I say F sub E, so we say the electric field force. That's fine. So what does this spell out to us? This spells out that we have the mass of the electron, M sub E, times its speed squared, divided by R, its orbital radius, that is centripetal force right there, has to be equal to K sub E times the absolute value of E minus times the absolute value of E plus, divided by R squared. E minus is the charge of an electron. E plus is the charge of a proton. We know what K sub E is, we know what M sub E is, the mass of the electron. And then we have R is the orbital radius. And some things that we should note here, M sub E is approximately 9.11 times 10 to the negative 31 kilograms. The absolute value of E minus is equal to the absolute value of E plus is equal to 1.602 times 10 to the negative 19 coulombs. And well, there was a correlated velocity and a correlated radial distance or orbital radius. So that was one postulate there. That seems cool. Fair enough. That seems reasonable. Well, there's some more things that go along with this that put things in a different perspective. So, second postulate starts to be on the more quantum type of side. And it basically says that light will be emitted by the hydrogen atom when the electron moves from a larger orbital radius to a smaller orbital radius. Light will be emitted by the hydrogen atom when the electron makes a transition from a higher orbit to a lower orbit. This light will be in the form of a photon whose energy proportional to the energy level difference between the two orbits. So what this basically says is if the electron moves inward towards the proton, there will be light emitted in the form of a photon. We'll get to photon here in a minute. And that light will have energy associated with it that is equivalent to the energy level difference between the states of the initial orbital and, well, the final orbital of the electron in the actual atomic system itself. So there's some more that goes along with this. Only discrete orbital radii are possible. This is putting a quantum sort of restriction on the system, saying that it just can't be anywhere. There are discrete locations, orbital radii or orbital paths at which the electron can exist. Those are the only stable orbits. Everything else, unstable, the electron doesn't exist there. So now it's saying, yeah, there's discrete orbital radii. And now we are looking at transitions between those discrete orbital radii. So this, again, sort of the quantum quantization factor that's being sort of embedded in here. Discrete, discrete, discrete. All right, so we'll come back to this photon. A photon is the smallest amount of light possible and is a particle associated with light. And it's not even really associated with light, it is considered the particle nature of light. Particle, let me not put it associated. Everything has both wave properties and particle properties. Light does too. Sometimes it behaves more like a wave, sometimes it behaves more like a particle, but ultimately it was understood to some degree that there was the ability of light to take on sort of particle properties. And photon energy, this came from Einstein sometime back before Bohr did all this. Photon energy, E sub gamma is equal to H times F, where H Planck's constant, come back to that. I gotta remember what that is. And F is frequency associated with the light. Drawing a blank on Planck's constant right now. It's been a while. It'll come back. It's a constant value. Maxwell Planck. Some cool stuff. Anyways, this is what we've got going on. This is a photon energy, and it was postulated that the energy of the light that is emitted is equal to the energy level difference of the actual hydrogen atom regarding the orbitals that that electron occupies and occupied. So now we've got this. E sub gamma, the photon energy is going to be equal to the energy level difference of the hydrogen atom. So we're going to call it E sub initial minus E sub final. And the reason that we're calling it initial minus final, because we're going from a higher energy to a lower energy, and even though the atom itself has lost energy, we're looking at the energy that it spits out in the form of a photon. And this just follows conservation of energy. The atom makes a transition between different energy levels, goes from a higher energy to a lower energy as it falls inward, and that energy is spit out in the form of a photon. So this is the initial energy of the H atom. This is the final energy. Of the H atom. And these energy levels are ultimately dictated by what orbital state the electron's in. All right. Yep, that was good. All right, so we've got that going on for us. That's great. So this kind of begs the question then, well, how do we tell what the energy levels of the hydrogen atom are? Energy levels of the H atom are given by the sum of its kinetic energy. We'll just say the sum of its kinetic and potential energies. All right, so what do we do with this? We've got E is going to be equal to K sub E plus P. So there's the total energy of the hydrogen atom. So let's investigate this a little bit more right now. We say, well, what's kinetic energy? That's 1/2 mv squared. What's moving here? It's the electron that's moving here. So let's say that this is 1/2 m sub E v squared. V is the speed, the orbital speed of the electron. M sub E is the mass of the electron. And there it is. And then we've got plus the potential energy. Well, how are we going to get potential energy? Is there potential energy? And the answer is, yeah, think about the potential difference between these two charges here. We got charged particles, we got sort of electronics to consider here. So we've got ourselves that we have an electron that is within the potential of the proton. That's right, that's right. So we've got ourselves plus, we've got E minus times delta V. I don't need to call it delta. E minus times V. This V is the potential due to the proton. Charge times the potential gives us the potential energy. So we've got ourselves V, in this case, is going to be equal to K sub E times E plus, that's the charge of the proton, divided by R, where R is the radial distance that the electron is from the proton. So what do we get out of this? Well, E here is a negative value here, because because it's the charge of an electron. Negative 1.602 times 10 to the negative 19 coulombs. And then we got V, yeah, there's V right there. But what can we do with this? Well, we can rewrite this slightly and say that this is then 1/2 m sub e v squared. And then we can say that it's plus k sub e, e minus, e plus, divided by r. Or we can group those two e's together and pull out the negative sign and just call it e plus squared and go with this. So this can also be written as 1/2 m sub e v squared minus k sub e e squared divided by r, where e is equal to the charge of the proton. So we just kind of factored out the negative sign here. So there it is in terms of the kinetic and potential energies. And what does this depend on? Well, again, it depends on the speed and the orbital radius of the system. Speed of the electron and the orbital distance at which it orbits the proton. All right, so can we do some more with this? And the answer is, yeah, sure we can, because we've got this correlation right there. Look at it. Something that has V and R in it. So let's go ahead and take this from the centripetal force being manifested by the Coulomb force and solve that out for V squared. And we can write that then as from this, we can write that V squared is equal to, one factor of r is going to cancel out, we divide that by m, and we've got ourselves k sub e. It's the absolute value of e minus and e plus, so we're just going to write that as e squared, k sub e, e squared, divided by m sub e times r. So that's how we can rewrite this velocity squared. And then what can we do? Well, we can put that in right there. That's right, that's exactly what we're going to do. And now we're going to say from this that E sub H, I guess we should be calling it, sub H, the hydrogen atom, is then equal to 1/2 m sub E multiplied by k sub E, E squared divided by m sub E times R, great, minus k sub E, E squared over R. Minus k sub e, e squared divided by r. One thing you should notice here, m sub e cancels out here. And we are left with then one, let's not even say one, let's just say this. We've got ourselves k sub e, e squared divided by 2r minus k sub e, e squared divided by plain old 1r. Well, look at this. What happens if we just multiply this by 2 over 2? We get ourselves a nice common denominator. So we can go ahead and do that. Times 2 divided by 2. And what does that give us? Well, it gives us k sub e, e squared over 2r minus 2k sub e, e squared over 2r, which will be equal then to negative k sub e, e squared over 2r. Look at that. So, that's what we get out of this. There is the energy of the hydrogen atom. What does it depend on? Well, in this theory, it depends on the orbital radius. That's it. We trace it all the way back to how far is the electron away from the proton. That's R. The further away it is, the more energy it has. There is something that is of interest here, and that's this negative sign. How can you have negative total energy? What this negative sign ultimately relates to is that this is a bound system. The electron is bound to the proton. In order to remove it from the system, we would have to give it enough energy such that it's no longer trapped by the proton itself. And that's what this negative sign represents. So we'll have negative energies, but as we look at larger and larger R's, those energies get closer and closer to zero. And when we're at zero, that is ultimately when we have no more bound energy. The electron's been removed. So the closer to zero we are, the more energy the system has. But that's just how this works out. At any rate, it still doesn't give us quite the quantization idea. It just kind of, again, relates back to orbital radii. But if we look back at one of the other postulates, postulate number 2, it said there's only discrete orbital radii at which the electron can orbit. So we need to be able to find out what that is. All right, so brings us to the last postulate, and this one says, I think I skipped numbering one, that's okay. The total energy was kind of the third postulate. Anyways, 4, we say that the total angular momentum can only take on discrete values. That are integer multiples of this. So this is called H bar. H bar because it's got a little bar on top of the H is H divided by 2 pi. And it comes up so often that they just say, hey, there's a factor of H over 2 pi, we'll just call it H bar. H is Planck's constant. There it is. H is equal to 6.626 times 10 to the negative 34 joules seconds. That is Planck's constant. Came back. All right, so H bar is just this divided by 2 pi. And again, that comes from Planck and Einstein looking at light and such things. Anyways, what do we have then? Well, this is saying that m sub e times r times v, there's the orbital angular momentum of the electron, or really of the system here. The mass of the electron multiplied by its speed, multiplied by its orbital radius. That is then equal to n h bar, where n is equal to 1, 2, 3, dot, 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 an integer value. This is the true quantization effect that Bohr put in there that ultimately gave him the right correspondence with all of this. So what we want to do is utilize this quantization effect, saying that there's only discrete things that can happen here, and this is the condition of that discreteness, and see if we can unravel everything here. All right, so we got that going on. Great. Let's see what we can do with this now. So we want to save this. And I wrote it again up there. So we've got ourselves a couple things going on. We want to express this in terms of energy levels that are ultimately correlated with n here, and we've got that v in there. So we already note that v squared from up there has to be equal to k sub e squared over m sub e r. I'll write that again. E squared is equal to k sub e squared over m sub e times r. And then we can do something with this over here. From this expression right here, we can write that v is equal to n h bar divided by m sub e times r. Great. And what else can we do with that? Well, we could go ahead and say then that v squared is equal to n squared h bar squared over m sub e squared r squared. And say, well, this is one form of v squared. Here's another form of v squared. These two things have to be equal, right? So if v squared's this and v squared's that, we must have then that k sub e, e squared over m sub e times r is equal to n squared h bar squared divided by m sub e squared times r squared. What can we do with this? You guessed it, we can solve this out for r. So solving this for r, the orbital radii, or radius of the electron, we'll move this one over here. That cancels out one factor of r. We can write ourselves that r then is equal to m sub e. I don't want to do too much and mess this up. So I get one factor of m sub e goes away from the top. We're left with n squared h bar squared. And we have it divided by an m sub e times k sub e times e squared. Squared goes down, k sub e goes down, m sub e goes up, cancels that one factor there, and this r came over here and cancels that one factor of that. Boom, that looks good to me. So there is our r value, r. And then what can we do with that? Well, we can stick it in right there. And that will give us the energy levels of the hydrogen atom. All right. So, after all gets kind of said and done here, we've got ourselves, r stays there. So we can now write energy levels of the H atom as E sub H is equal to negative K sub E, E squared divided by 2, that's great, multiplied by 1 over R. So 1 over R is going to be equal then to M sub E, K sub E, E squared divided by N squared, H bar squared. And what do we do with this? We go ahead, put some things together, and we've got ourselves M sub E, negative M sub E, K sub E squared, E to the 4th, divided by 2 N squared, H bar squared. And there is the energy levels of the hydrogen atom that are ultimately resolved down to R, resolved down to N, which has to do with R. We see how it's related back to R right here. But this is it. Everything in there is constants, except N can vary. N can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so on and so on. And what happens is N gets larger and larger. This value comes closer and closer to 0, representing higher and higher energies. When N is equal to 1, we've got the lowest energy that there is for the atom. And that's what we want to start looking at next, is how this is all sort of squished on down into those values. Ultimately, we can calculate what this is. We got the mass of the electron, Coulomb's constant, the charge of an electron, we got H bar there, and then we got this 1 over N squared that we can go ahead and put in this. And we can ultimately represent this E sub H is equal to, this is approximately negative 13.616 divided by N squared. But this 13.616 is in units of electron volts. And We've seen electron volts before. I'll go over that really quick here. But this is how it's generally written out, so that we know that as n increases, we get the energy levels approaching 0. This is an SI unit. It's not joules, but it's closely related to, and generally with atomic systems, we utilize electron volts as the preferred unit just because they're nice numbers, because this happens to be a really, really small number for a singular atom. But here we go. We've got that 1 electron volt is equal to 1.602 times 10 to the negative 19 coulombs. There is the conversion factor for electron volts, excuse me, not coulombs, joules. And ultimately, an electron volt is defined as the energy gained by an electron that's accelerated through a potential difference of 1 volt. Well, you say how much energy is gained by an electron that's accelerated through a potential difference of 1 volt? That's the charge of the electron multiplied by the potential difference of 1 volt. And that's how much potential energy would be lost, which is how much kinetic energy is gained. And there you go. You got yourself that conversion factor right there. Really convenient, based again upon the energy gained by an electron that's moved through a potential difference of 1 volt. The kinetic energy gained when it's accelerated through, or the potential energy gained when it's moved through. Gained or lost. Depends which way you move it, but there it is. Anyways, this is what we get here. And this is what we want to have. And that is a fantastic. So ultimately, what we can have here is that energy of the emitted photon for a particular transition is equal then to negative 13.616 electron volts divided by n initial squared minus negative 13.616 electron volts divided by n sub final squared. Where this is just correlated with the initial orbital radii, and this is correlated with the final orbital radii. And again, we're only considering going from a higher energy level down to a lower energy level where energy is released. That is in the form of the photon. Can go the other way, but that's energy absorbed. And ultimately, that's it. So we're going to come back and do some cool stuff with this and sort of map some stuff out a little bit better and see some other things. But this is all kind of extracted out of Bohr's theory of the atom here. Oops. One moment. Don't go yet, Do a little bit more. This is not 616, it's 606. My bad there. I put 1, but there we go. 13.606 electron volts. And there's one more thing I wanted to do before we transition into another video, and that is looking at what's known as the Bohr radius. So if we go back to one of these expressions, this one right here, this gives us the orbital radii of the electron based upon what energy level it's in, based upon what we're going to call the principal quantum number n. So this ultimately spells out to just a numeric value except for n. That's a constant, that's a constant, that's a constant, that's a constant. So when we go ahead and evaluate all of that, we find that R sub n is equal to n squared times what we'll call a sub 0. And a sub 0 is all of that other stuff. H bar squared divided by m sub e, k sub e. This is called the Bohr radius, because ultimately it's gotten with an n equals 1 value. It is the smallest smallest orbital radius of the electron. And thus, correlates with the smallest energy level of the atom. And if we go ahead and compute out what A0 is, A0 is equal to 0.529, I believe 0.529. I think that's right. And this is angstroms, another type of unit here. A with that little 0 on the top equals angstrom, and 1 angstrom is equal to 1 times 10 to the negative 10 meters. So that's, I don't want to say it's a prefix because it's not, it has units of meters, but it's 10 to the negative 10, and it commonly gets used for internuclear spacing measurements and such things. So it's a really small distance. The separation between the proton and the electron, when the electron's in its smallest energy level, known as ground state, is a little bit more than half of an angstrom. Pretty small separation, right? That's it. That's it. So that's something else that we can look at. As n gets larger and larger, the orbital radii get larger and larger, and we can kind of map this out then. And ultimately have this. We have, I'm going to need more room than that. Yeah, let me do like this. We've got this, and this isn't going to be scaled out, right? There's our proton, and then we're going to have the n equals 1 radio distance, and that could correspond with that a sub 0, 1 angstrom, and then the n equals 2 is going to be equal to 4 times that radio distance. So if this is 1, then I'd say, well, 4 times that 1, 2, 3, 4, puts us way out here. So there's the n equals 2 orbital radius. And then what do we do? Well, the n equals 3 is 9 times this. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's way out here. I'm not going to draw this to scale because that's just going to get crazy. But we've got something like this. N equals 3 orbital radius. And these correspond again to the energy levels too. This would be the energy level E1. This would be E2. This would be E3 with the electron occupying those states. The electron goes from one orbital radius down to another. Electron makes a transition to a lower energy level. A photon is emitted. So what do we get out of this? Well, this releases energy. We've got that the energy level of the hydrogen atom reduces. Energy can't just go away. It spits out a photon. So we got this. And the energy of that emitted photon, E sub gamma, would be equal to the energy level difference between these two energy levels here, which, well, we've already gotten. We could go ahead and compute those out and figure out what the energy of that photon is. And then, what do we have? Well, we've got the ability to say what the wavelength is corresponding to that energy, because, again, for a photon, we've got the energy is equal to Planck's constant multiplied by the frequency, but for any wave characteristics, we have the frequency is equal to We've got the wave relation V is equal to lambda F, which we can then say then that F is equal to V divided by lambda, and we can write this for light. C, the speed of light, and then we can write this then as H sub gamma is equal to, E sub gamma is equal to HC over lambda. And that is there, the wavelength associated with the emitted photon, which correlates with, well, if it's in the visible spectrum, a particular color of light. And we go back to what we first witnessed, that we had this hydrogen gas. We look at its light as it's passed through diffraction grating, and we see these discrete spectral lines. And those discrete spectral lines have specific wavelengths that correlate exactly with what Bohr has spelled out here. And that this successfully predicted the wavelengths of the emitted photons that are observed. And thus, I don't want to say the birth of quantum mechanics, but there was some deep rethinking the nature of everything from this point on. Quantum gets really crazy. Anyways, that's where we'll leave it. Looked at some extra stuff. What we'll come back and do in another installment is look at energy levels, sort of make a little bit more sense of all this. But this is kind of the outlay of everything. All right, now I'm going. Be well. Until next.